Hello students, it is nice to once again get back to the physics videos. Today we are going to start with a new chapter. The chapter name is Properties of Matter. So you know already matter consists of three stages, three groups, solid, liquid and gas. So we'll be studying about how this matter behaves in different scenarios. So under pressure, under different stress levels, how does matter behave? So that's what we are going to see. So one of the first one we are going to see is elasticity. So this is considered as a chapter 13 here in this, according to this book, but according to the actual syllabus given by ICSE or ISE, it is properties of matter. It is the 7th one. So syllabus is given here. Elastic behavior of solids, stress-strain relationship, Hooke's law, Young's modulus, bulk modulus, rigidity modulus, and Poisson's ratio and elastic energy. So we'll try to see all of them. This is mainly a numerical part of it. There are quite a lot of numericals will come in this part, right? So first of all, let us try to understand few of the terminologies. Deforming force. What is deforming force? Suppose if you have some kind of a body which is there, it is attached here, it is attached to this one. Now you apply a force, the external force, this force is called deforming force. You apply an external force, that is called deforming force. The external force which is applied to your body, which can cause any change in size, shape, and both when the force is called this deforming force. Alright. The next one is the basic thing of elasticity. What does elasticity means? We have a wrong idea about elasticity. Please, you need to understand that elasticity means, what do we know? When you take a rubber band is like this, and when you pull it, then it becomes so much longer, and that is called elasticity, we say. We have elastic in our many of the things, even the mask that you are wearing, that you have elastic which is trying to stretch it out, that is called elastic, we always say in words. But remember, that is not elastic. So anything which stretches is called elastic for us, but no, that is not the actual meaning of elastic. Now look at this one. Elastic is a property of a material by virtue of the body opposes any change in shape or size. What does elastic means? You try to pull this one, maybe you try to pull this body, or maybe there is a small thick rod is there, and you try to pull, give the force here, and this one, it doesn't immediately change. It provides an equal opposite tug and another F which creates in between. It doesn't change. So that is called elastic. Now look at this one. The elastic is material. The elastic is that property of a material by virtue of which the body opposes any change in its shape or size when deforming force is applied. Then opposing force is called the elastic behavior, and it tries to recover the original state immediately. It tries to immediately get back to the original state, right? So we'll again go on to the next part of it. The very important definition we are heading on towards, it is called, what is stress? This is a very common word we use in psychology, and as well as in these days. You are very stressed because of studies, you are stressed because of online exam things, and so many stress is there, and you are very much stressed. Stress, this is always talked in different connotations. In bodies also there is a stress. Any body also goes through any stress. So we're going to see what does it mean by stress. So if there is maybe any kind of an object you can consider, and you can see when you are going to give any force, what does that mean by stress. So let us consider a small tiny piece of rod is available of length, and this is the rod with the uniform thing, and you apply an external force. This is an external force is applied. So as you apply an external force on this one, maybe constantly you are applying a force. Now this rod is supposed to then immediately what will happen, different area of cross section which will have a constant internal force will be trying to pull this one this direction. Everything will be trying to pull, all the molecules will be trying to pull in this direction because you are given external force. But the property by virtue of this particular body itself, you will try to oppose the external force. I already said this one, there's an opposing internal force will be there. So it is called opposing internal force. Will be trying to pull this body inside. External force is applied, internal force is already trying to pull this one inside so that it will not have any deformation. So that is called stress. What is stress? Then opposing internal force for every area of cross section, per unit area of cross section, is called stress. So stress is called opposing internal force per unit area. That is called stress. You can call as F upon A. Stress can also be equal to, suppose if you got a deformation. Suppose you consider it has got a deformation here and it is in equilibrium. Now it is no more it is extending, it is just stopped there. So the external force, this F, is equal to the internal force. Because it has got deformed, it is now stopped deforming anymore, it is now static now. That is called equilibrium. It is called equilibrium. At equilibrium, what will happen, external force is going to be equal to internal force. So it's also called as stress. Can be equal to external force applied per unit area of cross section. That is also called as F upon A. So this is called small f upon A, this is capital F upon A also can be called. Let me read this one. The internal restoring force acting per unit area of cross section of the deformed body is called stress. So how it is there? Because of the internal reactionary force is developed in the direction opposite to the applied force, which tends to restore the body in its original state. That is the internal restoring force would be there per unit area. In equilibrium, when it is got equilibrium, the restoring force is equal to the magnitude of the external force. The restoring force is equal to the external force. So you get this one. Stress is equal to F upon A. Now stress is also called as force per unit area. It's called pressure also. Pressure is also equal to force per area. So you can mention that way also. So it is called Newton per meter square is a unit. Right? And then what is the dimension here? So you know the dimension mlt minus 2 upon L2. So it's going to be ml minus 1 t minus 2. Right? Okay. The next one. We are going to the next very important thing called strain. We are going to read the next part called strain. So what is strain? Strain means change in shape upon original shape. That is called strain. Strain is just a ratio of the change in shape to the original shape. So suppose if there is any kind of a change has happened per unit original size of the body, then that is called strain. So strain can be of three varieties. Strain can be of three varieties. One is called longitudinal strain. What is longitudinal strain? It is going to be called as the change in length upon original length, volumetric strain. What is volumetric strain? Change in volume upon original volume. The next is called shearing strain. It is theta is going to be equal to delta L upon L. These all three things we will try to learn little more detail when we see different modulus accordingly. Okay, I'm not just going to explain everything now itself, but there are three things. So you can write down the definition now. Strain. So what does strain means? Strain means the change occurred in a unit size of a body is called strain. Unit size of the body. Change per unit size. What are the original size? So there are three things. Please write down this one also and the formula also. Okay. Now let us go to the next part called modulus of elasticity, and it is given by a law called Hooke's law. There was a scientist called Hooke's law. He said within elastic limit, there is a condition within elastic limit, the stress on a body is directly proportional to the strain developed on the body. You give stress because of the external force, the stress given to the body is directly proportional to the strain developed on the body. Please write down within elastic limit, the stress is directly proportional to the strain. So what is that stress? Equal to E times of strain, that is proportionality constant. What is called? It is E. So E is going to be called as stress upon strain. What is E? E is called modulus of elasticity. Modulus of elasticity. Now the word called elasticity is coming more clearly. What does elasticity means? The ratio of stress to the strain. Now we already had seen stress. What is stress is called? Force per unit area. What is strain? Change in shape or change in length upon original length. Original length delta upon L or delta V upon V. So this two ratio, it is called modulus of elasticity. So different bodies has its own modulus of elasticity depending on the stress strain ratio. This is called Hooke's law. This is called Hooke's law. Hooke gave this law and it is named after him. But the condition is, what is the condition for a Hooke's law? Within elastic limit. Everything should happen within this limit. Beyond this limit, this is not proportional. You cannot command and demand this proportionality if it is not in limit. Alright, so that's quite important here. Let us go on to know the graphical representation on stress and strain, how much proportionality happens. Okay, you're going to draw a graph, how it moves, how this one develops over the course of time. Alright, let's see that one. Alright, so we are going to see elastic behavior of a wire, and you're going to see the graphical representation between stress and strain. How does stress and strain behave? Let us take a small wire. This is just a thin wire which is there of a particular length L, and you give an external force. We all know how to give external force. Just give external force, then the wire extends. So the delta L is a change here. The delta L is a change in the length over here. Till this point, there is a length has got changed. Alright. Now, once this is changed, you leave the force. Just leave the force here. This wire will come back to this original position. So it's so important, whenever the extends, you leave this external force. The external force is removed, it has to come back. Suppose you extend a little more beyond and you leave it. Sometimes it doesn't come back at all. It is already permanently deformed till this place. Have you seen sometime? You extend the rubber band beyond and you leave it, and it will not come back to the original place. It will be there already set as a deformed body. Now what happens if you just further extend, further pull it more? Then what happens here is, it goes on a behavior that this will become very, very much inelastic. It doesn't come back at all, and also at one point of time it can break also. Let us see the graphical representation. So draw a graph and write here stress, and this is strain, and this is the origin O. So this is X and Y. So the first thing is, when you apply a stress, force on a per unit area, immediately strain happens. So the force will be applied, and it is directly proportional. We already know stress is directly proportional to strain. Now what is the condition here? Elastic limit. So we already know stress is directly proportional to strain. That means it should be a straight line graph. So you get a straight line graph from O to A. From O to A, you get a straight line graph. Stress is proportional to strain. You increase the stress and automatically strain also happens. You leave it, immediately it goes back to the original position. That's what it is. So it is like that. So point A, or you can say OA. So this point OA is mentioned as, what is the region? OA is called elastic region. So you can say it is a place where the Hooke's law is obeyed. Elastic region and Hooke's law is obeyed. The next thing is, give beyond this one. Beyond this one, you take this one. So it goes for a little bend and it goes till B. And this point B is quite important here. So the point B is called elastic limit. B is called elastic limit. That means you are just really going to the maximum limit now. You cannot go beyond this. Listen, you keep on giving stress, then that particular body can take only that much. So it is B is called elastic limit. Look at this one. It is no more having a proportionality is now getting little more change. Now look at this one. This is what elastic limit means. B is a point of elastic limit. Within the elastic limit, stress is directly proportional to strain, right? So this entire region is called elastic region. You can say even OB. Also you can say it is elastic region. Then afterwards, you will find the part of the graph, it goes for a little more change here. It goes to further change here to another point called C. Now point C is called yielding point. Yielding point. Yielding point means you just give a little more stress and it goes to this point called yielding point. And if you leave it here, if you just leave it the body here at yielding point, the body will not trace its original position and come back to zero. It will come to this particular point. So it is called O dash is called permanent set. Permanently it is settled with the elongated one. So it is called O dash. It will not, after yielding point, you just release the stress, release the force, it will not come back to this part, it will come back here like this. And O dash is already permanently deformation will happen. The next one is, after this one, then again you keep giving this one, it slightly goes up above and you find a point D appears here. A point D appears here. Now look at this one, it just goes on a flow now. It is just flowing in, the strain is now really going fast for a small amount of stress itself. Very small amount of stress, it just goes here and it does a point called D, it behaves here. Now what is this D here? The D point is a place where it is really getting more, the maximum value. The point D is called the stress reaches the maximum value. So that is called the maximum value of stress. Beyond that, you could have never gone beyond that. Okay, you can do, please don't go beyond that. So that's what it is saying. It is the maximum value here. After that, sometime it just drops down and it goes to E. And point E is a point where it is called breaking stress. Breaking stress. It flows so fast and then it will finally breaks. E is a breaking stress point. Okay. Now you got a lot of points to understand. So OB is called elastic region, and it is exactly Hooke's law is obeyed here, and slightly it obeys here also, so it is called elastic limit, and Hooke's law is obeyed, so it is called elastic region. Afterwards C is called yielding point. You release your force and it comes to this position, it's called permanent set, and it flows so fast and goes to D point. There is a maximum value of stress, and afterwards a yielding breaking point, it finally breaks. Draw this diagram, write all of them. It will be pretty useful. Please read this one carefully. Whatever I have told, it is given here carefully, nicely. Hooke's law is obeyed, OA, so limit of proportionality. And the next one is, reading the book is so important. Please read this one at B. And then next one is, B is called elastic limit. So the stress at the point B is called elastic limit, and then elastic limit is close to the proportionality limit, and then elastic region is there, and then yielding point, I already said, yielding point is called C point, and then it comes here to O dash. How does it happen? That's also given here. And then C point is, beyond C point you will find the thing, it's called reaches the maximum value, stress reaches the maximum value, and then finally breaking point is there. Then breaks it into two pieces. So this graph and then the explanation is so important. Please read this lines and then write accordingly. Now we'll go to the next few definitions here according to the modulus of elasticity. So the next section we are going ahead of seeing modulus of elasticity. There are three modulus: Young's modulus, bulk modulus, rigidity modulus. All three has a slight difference in the formulas, but remember all of them, it comes from the basics of Hooke's law. What is Hooke's law? Elasticity, the modulus of elasticity, E is going to be equal to stress upon strain. This is the basic Hooke's law. Under Hooke's law you get E. What is E? Modulus of elasticity. Under the modulus of elasticity you are going to have three: Young's modulus of elasticity, bulk modulus of elasticity, and rigidity modulus of elasticity based on Hooke's law. Alright, so let us go ahead and see one by one. Number one. So the first one is Young's modulus. So when does Young's modulus take place? Young's modulus takes place mainly when there is a length is involved. Only the length is involved here. Not volume, not anything else, length is involved. And you give the force here, and it makes a change here called delta L, because you give an external force. So there is a slight area of cross section, maybe there is an area of cross section called capital A, because whatever the thickness is there, but length is now, it is getting changed from length to another length, it is getting changed. So the Young's modulus of elasticity is the ratio of longitudinal stress to longitudinal strain. So it is called stress upon strain. In other words, it's also called as the normal force, the normal stress. You need not say always longitudinal, it is a normal stress upon longitudinal strain. It is longitudinal stress upon longitudinal strain is called, what is this called? It is called Young's modulus. You can say Y, Young's modulus of elasticity. So let us see what is longitudinal strain. So longitudinal strain is strain, longitudinal strain is going to be equal to force per unit area. Alright, now next one is longitudinal stress. I'm sorry, it is called stress. Now this is also can be called as mg upon area of cross section, because suppose if you are pulling out with a weight, then it expands. it expands, and then still the weight is there. So this is the delta L value. So it is called mg is there. Now next one is strain is going to be equal to delta L upon L, because it is longitudinal strain, delta L upon L. So what is the modulus of elasticity? E is going to be equal to mg upon A upon delta L upon L. Instead of E, what you will write here? You will write Y. So Y is going to be equal to mgl upon A into delta L. What is this A is called as? Because this is going to be a kind of a circular one. So mgl upon pi r square into delta L also could be considered. Now what is the SI unit of Young's modulus? Young's modulus is going to be equal to, now you get here force upon area. So it's going to be called as N Newton per meter square upon no unit. What is no unit? Length upon length, no unit, Newton per area. So it is also is called as Newton per meter square. In other words, also you can see the dimension here. What is the dimension? Similarly of this one, m l minus 1 t minus 2. That's the same dimension you will get here. Alright. So let us look at this one. Longitudinal strain, stress is going to equal force upon area, mg upon pi r square. Strain is equal to increase in length upon original length, delta L upon L. Now Young's modulus of material is going to be equal to this formula, mgl upon pi r square delta L. So that's what you get here. So mgl upon pi r square delta L. Now another very important interesting question it comes is, which is more elastic? Steel is more elastic than rubber, or rubber is more elastic than steel? Always till now you have got an idea, rubber is more elastic, steel is not elastic. But look at this one, we will consider two of them. We will consider two cases here. Now the same formula is now, it is already written here. The same formula is there. Young's modulus of steel Ys is going to be equal to mgl upon pi r squared delta L. And then Young's modulus of rubber. Young's modulus of rubber, mg L upon pi r square into delta L. Now look at this one. Let us consider two wires of, one is steel and next one is rubber. So look at this one. There is one is a steel wire, next one is a rubber wire. Same length, same force you give, same force you give of mg on both of them, and same area of cross section, pi r square is same. Now what happens here is, whenever you, as soon as you start putting a weight, which will extend more? Do you know which will extend more? Rubber will automatically extend more. It will give this much of delta L. And what happens to steel? Maybe it gives us very small, maybe very little. Now delta L of rubber is so long, delta L of steel is very less. So delta L of steel and delta L of rubber. That is what this whole thing is. Right, delta L of steel is very less. Now we take the ratio. Now look at this one. Please make sure this is delta L of steel, delta L of rubber. So the delta L of steel upon the Young's modulus of rubber, if you look at this one, it is going to be equal to delta L of rubber and delta L of steel. It's kind of as a ratio here. So which is greater? Delta LR is greater than delta LS. So therefore, which Young's modulus is greater? Now this is greater. Therefore, Young's modulus of steel is greater than Young's modulus of rubber. So Young's modulus of steel is greater than Young's modulus of rubber. Now with this thing, If this is more greater and this is less, so which is more elastic? Steel is more elastic. Because Young's modulus is greater. That is the reason steel is more elastic than rubber. Please remember that one. Steel is more elastic than rubber. Remove that idea of rubber is more elastic than steel. Suppose you drop a steel ball and a rubber ball, same size, on the floor. You know which will rise more? Steel ball, after bouncing back, it will rise more than a rubber ball, because rubber ball will have lot of deformation. This will not deform at all because it is very rigid and it will quickly rise up. This will not rise up fast and it will have much definitely a lesser this one. Okay, if you have ivory and all, ivory is much more higher in Young's modulus and it will bounce much more higher than. Alright, hope you got the idea. Now note is also quite important. Please note down. So this note, so a small solid balls of different substances dropped. Okay, so what will happen? You drop an ivory or rubber or wet clay, which one will rise ahead? You will be able to read this one and understand. Okay, so that's quite important. Let's go to the next part. The next one is Young's modulus is over bulk modulus. So let us continue to see what is bulk modulus is concerned. Now you need to draw a diagram like this. So write the topic here. Second one is bulk modulus of elasticity. Consider this is the cubical body and start applying force. Everywhere force is coming. Nicely force is coming. So here also, and then opposite direction also, everywhere force is coming. You can call it as pressure also. Force per unit area is pressure also. Everywhere pressure is applied. Now because of that, this entire thing, it went on to a smaller size of the body. What happens? This became smaller in size. What happened to this length? It's all changed. Everything is now compressing. As it compresses, it became smaller in volume. So, what is the first change, visible change that you are taking place is, it is called change in volume. Change in volume to the original volume. What is this called as? Volumetric strain. That definitely takes place. Why it is taking place? Because of the stress. It is called as force per unit area. Alright. So volumetric strain is there, stress is there. So bulk modulus is going to be equal to, what is the volumetric strain here is, look at this one, it is minus delta V by V. So it is going to be called as minus delta V by V upon force upon area. We can write it as pressure itself. Right? So this is called as K. So K is going to be equal to P delta V upon V, that is minus, this is called bulk modulus. If you have a balloon, you all play with the balloons when you are small and you apply force all directions and it deforms and brings into a smaller one. What is this one? This is a new volume here. Alright, the first one is bigger one and then now it is gone to the new volume. So it is called, you can also call this as change in volume to the original volume. Simple as that. It is already given here. You can understand. So look at this one. Bulk modulus is equal to normal stress upon volume. So, okay. I think I made a big mistake. I made a very foolish mistake. Please cancel this one. This is not correct. Why it is not correct is, what is bulk modulus? What is the modulus of elasticity? It is called as stress upon strain. Okay, this is what the basic formula is. What is stress? We call it as pressure. What is strain? It is delta V by V. So this one is not there. What is bulk modulus? K. K is going to be equal to stress upon strain. What is called strain? What is stress? It is called normal stress. Normal stress upon volumetric strain. So it's going to be called as P upon delta V by V. So it's going to be called as PV upon delta V. I'm very sorry, this is wrong. This is the right one. So there is a negative point. There is a negative. What is there is a negative one? Negative of delta V upon V. Because the volume is reducing. The volume is compressed. So the change in volume is a reduced volume than the earlier one. So delta V. So that's the way it is. Now you can ask a question, sir, okay, the volume is reducing, fine. Sometimes the body also swells to a bigger portion. What happens? There is some expansion is there. This is the original one. This is the original volume. Now you got a changed volume. Bigger one is there. Then what happens here? Now what happens here is K is going to be equal to, so yes, of course, delta V by V is a positive value because your changing in volume is positive. But remember, the stress which is happening, the normal stress will be a negative value. Why it is negative value? Because it is going in the opposite direction here. Earlier, all of them were going in inward direction, so it is a positive direction. But now it's all going in opposite direction, so it is minus P. So because it is changing, it is expanding, doesn't mean your K value will be positive. It will also be negative here. So it's going to be again minus PV upon delta V will be there. Alright. So hope you will understand this particular part of it. So let us see the book also. Yeah, normal stress upon volumetric strain, P upon delta V my V, PV upon delta V. Now look at this one, compressibility. What does compressibility means? Compressibility means it is beta is going to be equal to 1 upon B, 1 upon bulk modulus is going to be called as minus delta V upon PV. So in the note says if P is positive, alright, the normal stress is positive and delta V is negative, then and if P is negative, delta V will be positive. Now that's what I said already. Look at this one, that's what I said already. Here, this is negative, this is delta V is negative. So you got the bulk modulus also negative. Bulk modulus was the value of negative. And the next one is P is negative and this is going to be positive. Again, bulk modulus will be negative. We'll go to the last part of it. What is the last part of it? Now, Young's modulus we done, bulk modulus done, rigidity modulus. What is rigidity modulus? Let us consider, okay, so write down third part of it, rigidity modulus of elasticity. So let us consider a body like this and it is attached to the fixed ground, nicely attached, firmly attached. Give an external force in this direction. If you give an external force in this direction, top direction, bottom part is all fixed. Top direction, when you give a force, what will happen? This will immediately deform. So it will again deform like this. And it will be theta, here will be a deformation. And so there will be theta here, there will be theta here. So when there is a deformation like this, then it is called as shearing strain. What does shearing strain means? Shearing strain means L is equal to, this is delta L change will be there and this is the length. So this is delta L upon length. So that is called theta is going to be equal to delta L upon L, that is shearing strain. And the next one is you are giving an external force. The force given, or is going to say the stress is called the shearing stress. What is shearing stress? Only in the tangential value you are getting the stress here. So once you got the stress along the tangential value only, so what you get here at the end of the time, So it's going to be stress is going to be equal to, shearing stress is going to be equal to force per unit area. So rigidity modulus, it is called as eta is going to be equal to shearing stress upon shearing strain. What is shearing stress upon shearing strain? It is going to be equal to F upon A upon theta. So it's going to be equal to F upon A upon delta L by L. So it's again the same way. It is going to be equal to F L upon A delta L. That is eta. Alright. So this is the way in which you will get. Right, now look at this one. Modulus of rigidity. So it's called as, now look at the definition. Please write down the definition: the ratio of displacement of the layer in the direction of the tangential force. So you start here, and the distance of the layer from which the fixed surface is called the shearing strain. And the tangential force acting per unit area is called shearing stress. Within the elastic limit, up to Hooke's law is applicable, the ratio of the shearing stress to the corresponding shearing strain is called modulus of rigidity. Please write down till this much, it is so important. And then the derivation whatever I have derived, and you get the same answer here. So you get the same answer here. Eta is going to be equal to F upon A upon theta. Alright children. So we have done this one. The rest of them you will see in the next class. Thank you.